Our final topic that we're going to discuss for atomic spectroscopy is the presence of interferences and what we can do about them. There are three major kinds of interference in atomic spectroscopy. The first type of interference is spectral interference. All right, I accidentally moved that. Okay, so spectral interference is overlap of our analyte signal with other species or with light from the flame. Now, I will say this is much less of an issue in atomic spectroscopy when compared to molecular spectroscopy. With molecular spectroscopy, because of the wide bandwidth of the peaks, the wide line widths, we often will see multiple things absorbing at the same wavelength. And that's essentially what we're talking about here, is that if we make a plot of, we'll look at absorption, for example, here, versus wavelength. If we have two elements where we get an overlap here, that can cause an interference in our measurement, right? So if we have, say this is manganese and this is iron, or something like that, if we have iron in our sample, it can affect the results that we get from our manganese measurement. So, you know, even though these lines are very narrow, some atoms have a lot of absorption or emission peaks. Iron, for example, is pretty crazy with this. There are peaks all over the visible and ultraviolet range. So even with these very narrow line widths, you can still have overlap that happens. The easiest solution to get around this is to find wavelengths with no interference. Because pretty much all atoms have many different wavelengths that they will absorb or emit light at. And so you have your choice. You can find something that's far away from anything else that's going to be present in your sample. So find wavelengths with no interference. And because you're using a hollow cathode lamp, you can produce light at whatever wavelength you choose, right? So that'll work. And these are often pre-selected, right? These have been analyzed in advance so these are often pre-selected in the AA software or in the atomic absorption software. So you can select, the particular wavelength that you want. One other possibility to get around this is to measure sample at multiple wavelengths that correspond to your measurement, correspond to your atom of interest. And if any of them look weird, you know that there's some interference happening there, and you just throw out those data. So you should get the same result no matter which wavelength you choose, and this gives you a way to measure a bunch of wavelengths and see that they do all correspond to each other. And anything that doesn't, then you can know that they're you can throw out that result and use everything else. So that is interference number one. Interference number two is chemical interference. Spell it correctly, interference. And this is some sort of interaction of your sample and analyte that prevents atomization. So one of the assumptions that we make with atomic absorption or emission spectroscopy is that we get a consistent fraction of our atoms that are atomized. Ideally, all of it, but in practice, there's always some that don't atomize. And so the sample we have needs to be in its constituent atoms. It can't be complexed or attached to something else, because that will affect the spectral lines that we see. It has to be in the atomic form in the gas phase. So as an example of something like this, sulfate or phosphate will hinder calcium atomization. by forming very difficult to atomize solids. I'm not sure the exact process. So what can we do about things like this? Well, we can protect the calcium. Protect calcium with EDTA to prevent reaction with these, because the EDTA will complex the calcium, and the EDTA will be burned up in the atomization process where the sulfate and phosphate won't. Or you can add something to react with the sulfate and phosphate. And this is just one specific example. This is the sort of process you would go through for other atoms as well. All right, add something to react, like lanthanum with sulfate and phosphate. So you basically get rid of them, and they won't cause any additional interference. One other possibility is to run at higher temperatures. So, if you put more energy in, even when these chemical interferences happen, you can sort of, if you put in enough energy, they'll still break apart and turn into atoms. So run at higher temperatures. So you can use things like change your fuel and oxidant mix that you're using for a flame, or use an ICP instead of a flame to get higher temperatures. And that will promote atomization and reduce this interference. The final type of interference that we can have is ionization interference. So with all of what we've talked about at this point, we are looking at atoms that are not charged, right? We're looking at gas phase, metals typically, not ions, right? But some atoms will very easily, in the gas phase, give up an electron and turn into their positive ions. And this ion has very different spectral properties, because the energy levels are not the same for the ion versus the atom, because you've gotten rid of an entire electron, and so it changes all the energy levels that are present. So the wavelengths at which it absorbs and emits light are very different than for the neutral atom. So if you produce a significant fraction of the ion, it's going to affect your results. So in particular, things like alkali metals have very low ionization potentials, which means that this is much easier to happen. Easily ionized. And we ideally don't want the ionization to happen. And we want to sort of suppress this and get rid of this. And so in things like this, we could add a cesium salt to suppress ionization. And the purpose of this, cesium is one of these alkali metals, and it is the one that has the lowest ionization potential as the largest alkali metal. And so it will preferentially ionize, and that will produce extra electrons, which, according to Le Chatelier's principle, if we have extra electrons here, it'll push this equilibrium to the left. So cesium will preferentially ionize. It's the element with the lowest ionization potential, and will decrease the amount of ionization that's happening in your sample. And of course, with any of these interferences, I'll just remind you that standard addition, if any of these matrix effects are happening, standard addition is an excellent technique to help account for these interference effects in your sample. If you can't get around any of them, you can still use standard addition to help take advantage of, to help account for this in the process of your measurement. So we'll have one final video for this chapter, just looking at the different methods and their strengths and weaknesses, and that will finish it up for chapter 21.